Good morning and welcome to Computer Science 221. We're in the middle of our discussion of addressing modes. So far we've talked about PC relative addressing. And you may recall there was a load command and there was a store command. And here's a little mnemonic for remembering how this works. Ultimately, we're going out into memory. And the question is where are we going? And we're going to PC plus offset 9. You may recall the offset 9 is a 9-bit signed integer that is stored in the instruction. This is either where we go out to memory to load into a register or where we go out to memory to store something that was in a register. The nice thing about doing things this way is we found that this permitted relocatable code. The downside of this thing, I don't know if I'd call it a downside, I'd call it a limitation, is that this address had to be located within plus or minus 255 words of the PC. Okay, so again, to draw a picture of this thing, for example, if this was the load instruction right here, so remember, if that's the load instruction, then the PC is here. The PC is referencing the location right after it as we're executing it. We are limited in going either this way, 255, or going this way, 255. Okay? Well, the next one that we're going to talk about here, it's going to look a little similar, a little bit different. It's what's referred to as indirect addressing. So this either goes by what's called LDI, load indirect, or STI, and that's store indirect. And we're going to find that the actual machine code, or the format for these instructions, is very similar. First of all, this has an opcode of 1011. This has an opcode, whoops, that is my mistake already. This is 1010. This is 1011. And again, let's just consider the case of the LDI. So there's going to be a 1010, and then there is going to be a register specified here in 3 bits. And then again, there's going to be an immediate 9 here. So this looks very, very similar to the load instruction. The store indirect is going to look the same as well. But here's what is different. And this is going to seem a little unusual at first, but it turns out that you've all been doing this actually for a very long time. So, for example, here is the LDI here. So you may recall that means that the PC is over at the next instruction, right over here. Okay, and there's an immediate 9. So again, that means that I'm going either plus or minus 255. So let's just imagine that we're going down this way. And I'll just say that it's plus K where k is less than or equal to 255. And then what's happening in here is this is now the actual address. Now remember, this is a 16-bit quantity, and we recall that the address space of all of memory is 2 to the 16th. So now I'm going to put a little 1 over here because that's what we have to do first. Now what we do from here is now we can go anywhere in memory to get the actual operand that we're looking at. So maybe it's pointing over there. So it looks something like that. So the benefit of this is we can address anywhere in memory. Okay, and the downside, it takes longer. And why does it take longer? Well, think about what's involved here. First of all, what we have to do is we have to take the PC and we have to add this offset. We have to stick that number in here. We have to calculate this address. Then from this address, we have to calculate this address. We're going to go through the steps a little later on. But the point is to actually execute this instruction is going to take longer than it's going to take to do things when we're using PC relative addressing. So let's come up with an example of this just to get an idea of what's going on. So let's say I've got my registers over here, and let's say I've got R1, R2, R3, and let's suppose for the moment these have zeros in them. Let's come over here into memory. And let's suppose this is 3000, 3001, 3002, 3003. Let's skip down here a little bit. Let's suppose I'm down here at 3000A. And let's suppose in location 3000A, I have, let's say I have C000. And let's go way down in memory. Here I am at C000. And let's suppose I have 1, 2, 3, 4. Okay. And let's suppose I want to do the following. I want to do an LBI into register 3. Okay. And I want to use this as my ultimate reference down to here. I think you can see that this is a reference down to here. And let's suppose that this instruction is going to be at 3002. Now I come back over here and I see that the load indirect is 1010. So this is going to be a 1010. And it's going to be into register 3. So I'm going to go 011. Okay, that's 3. Now remember, when I'm executing this instruction, the PC is at location 3003. and I want to get from location 3003, I actually want to get this, 3000A. Remember, A is 10, so to go from 3 to 10, I have to add 7. I have 9 bits to do this. And then I'm going to go 0, 1, 1, 1. 1 plus 2 plus 4 is 7. So this instruction right here is going to be in 3002. That's an 8, 9, 10. That's an A. This is, over here, it's a 2 plus 4 is a 6. This over here is 0s, 7. So over here in location 3002 is A, 6, 0, 7. And what's going to happen, remember what happens when I execute this. Let's get another. Okay, so what's going to happen over here is remember the PC, when that executes, is going to have the number, let me move this out of the way. When the PC executes, when this executes, the PC is going to have 3003 in it. And what's going to happen is the instruction register is going to have A607 in it. Okay, so what is going to happen is first of all, you may recall, we've got the IR, and we have these 9 bits over here that are going to go into a sign extension register. So when I sign extend it, I'm going to get 0007. And now what's going to come is that's going to come over here. And ultimately, it's going to get added with the PC. Okay, and when I come out of there, that's going to get loaded into the MAR. And in this case, that's going to be a 300A. And then what happens is we're going to go out and we're going to read memory. So something gets into the MDR. Okay. And remember, what we've done at that point is we've read C000. I'm going to run out of space here. So the MDR is going to have that 3 or that C000 in it. And now what do I have to do with that? I have to put it back into the MAR. And then I have to access, I'm going to go this way because I'm running out of space here. I have to go back to memory. Okay, and what's going to happen here is now into the MDR is I'm going to get 1, 2, 3, 4, the memory data register. And then that is going to go back to register R3. So the end result over here is that in R3, what I had clicked the register, this, there we go. I now have that. So we can see here the difference between the indirect addressing and the PC relative addressing has to do with the fact that we had to go through this twice. When we were doing PC relative addressing, we would have had the desired thing right after we did this read here. But when we did, after we did this read here, we had to use the value that we read to go back into memory. In other words, what we had to do, and this is probably not well labeled here. I wouldn't call that the MDR. This is memory. And this is memory. Indirect addressing causes us to go read memory twice, whereas PC relative addressing only permits us to do it once. Now, this may seem weird, but it isn't. But you've been doing this for a while. Consider a Java program. And suppose in my Java program, I have some public class foo. And I come over here, and here's all the code for foo. I don't particularly care about it. But now let's go, we come over here, and I have my public static void main with all this other nonsense over in here. And I come over here and I say foo, my foo equals new foo, and I put something in here in the constructor. Okay? Now what's going on over here, if we were to take a look in memory, over here in memory, we have declared a variable called myFoo. That corresponds to some memory location here. I have no idea where it is. But now when I say new foo, what that's doing is that's going out somewhere else out in memory. Maybe it's coming right over here, and it's actually allocating the space. Here is the actual foo. The actual foo is right here. And maybe this is at location y, 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 y. And what we put in here is we put that address. Okay? But in your program, you say things like myfoo dot something. When you're using this thing over here, it's an indirect reference. It's coming over here and it's saying, gee, the number that's contained in here, this isn't where the actual variable lives. This is the address of where the actual variable lives. And it takes us down to there. So in Java, I'm going to say all objects are referenced indirectly. Key point. And again, and I'm going to keep repeating this because this is the way to, I think, to really keep it easy. PC relative. We're talking about mem of PC plus offset 9. Indirect, it's memory of memory of PC plus offset 9. Okay, have fun.